Greetings. So, we have come a long way in our discussion on the Hartree-Fock self consistent field formalism, and I had mentioned in our previous class that a student in a similar class had done a project on this. This is a report on that. So, this is from IIT Madras MSc Physics report of V. Lakshmi, who developed a Fortran code to get the Hartree-Fock self consistent field solutions. And in fact, the full report is in this. It includes the program that she wrote. So if some of you would like to try it out, you are welcome to do that. Essentially what we have learned so far is that we recognized that the Hartree-Fock equation is in fact a condition which must be satisfied. It is a necessary and sufficient condition for us to reach our goal, and our goal is to get self consistent field solutions to the n electron problem, and we do so by using the variational technique, by seeking an extremum of the expectation value of the Hamiltonian in the antisymmetrized wave function, subject to the constraints of normalization and orthogonality, and the condition that emerges is what we call as the Hartree-Fock equation, which is actually a family of n coupled integral differential equations. And there are a couple of questions that we raised toward the end of the previous class. We asked if this is an eigenvalue problem. It has some resemblance to an eigenvalue problem, so we need to study this in some detail. And then we want to ask how the formalism, how the Hartree-Fock theory connects to experiments, because at some level the main purpose of doing this is to see how it connects to experimental observations, and there would be some sort of physical connection between the theory and the experiment, so that these questions are the ones that we shall take up for discussion today. So, to answer these questions, let us begin with a look at the Hartree-Fock equation that we got in the previous class. This is the Hartree-Fock equation in the diagonal form, as you will remember. This is in the basis in which the matrix of Lagrange parameters, the variational parameters, is diagonal, and we will do a little bit of simple rearrangement of terms to extract some very interesting physics out of it. So, you multiply this by the complex conjugate of ui function, the ith function, and then integrate over R1. So, that is what we have done here. You multiply this first term by ui star R1 and then integrate over the volume element for V1, and you do the same for the remaining terms as well. Okay. So, every term is treated by the same prescription, and you find that here you get the normalization integral, which is equal to unity. So, the right hand side is a very simple one, and the rest of the terms we will handle very carefully. So, the first term that you get are the 1 electron integrals, and then you get the 2 electron integrals, because there is a double integration over V1 and V2. V2 was already there, and now we have included an integration over V1. So, now you have the Coulomb and the exchange integrals coming from these double integrations, right. So, let us look at this form. Now, let me remind you that the 1 electron integrals can be written in a more compact fashion in the Dirac notation. So, we will go over to the Dirac notation, because then it is much nicer and easier to write the relations. Likewise, the 2 electron integrals, the first is the Coulomb integral, which is sometimes called as a direct integral. So, this is the Coulomb integral. We have spent considerable time discussing this. So, we have got the Coulomb integral, which is I j g I j, and then we have the exchange, which is the 2 electron exchange integral, which is ijg ji. So, that is the notation. This will remind us that this is an exchange integral. Okay. So, these 3 terms appear in the equation that we got. So, this is the Dirac notation, this is the IFI matrix element, this is the ijg ij, and this is the ijg ji. And in terms of these, the Hartree-Fock equation which we got can be written in a rather simple compact fashion using the Dirac notation. And now the next thing I am going to do is to sum over the index I. So, this equation, there is such an equation which holds for every I goes from 1 through n. So, I sum over all the terms from 1 through n. So, I going from 1 through n is summed over on the right hand side as well. So, here we are, this is the summation of those terms. The Coulomb and the exchange terms are summed over both I and j, the other terms are summed over only the I index, and this will remind you of the expectation value of the 1 electron operator and the 2 electron operator. These expressions we had obtained earlier, and the expectation value of the 1 electron operator is sum over I going from 1 through n of this matrix element, which is what you find over here. So, this is obviously the expectation value of the 1 electron part of the Hamiltonian. This is somewhat similar to this, but not quite, because there is a factor of half here. If you sum these two, what would you get? You would get the energy of the system, right, because you will get the expectation value of the Hamiltonian in the n electron system. So, you would get the energy by adding these two pieces, which is this over here, and it is not quite equal to what you get from this equation. So, the sum of I going from 1 through n of these epsilon I, which came as the diagonal element in the matrix of the Lagrange matrix, right, that if you add up all of those, you do not really get the total energy of the n electron system. What is the difference? You have got a factor of half over here, whereas over here this multiplier is unity. So, if you take this expression and add to it another half, then you get the left hand side of this. So, that is what you have. You take the expectation value of the Hamiltonian, add to it the expectation value of H2, and that is what gives you the right hand side, which is the sum of these epsilon I which appear in the Hartree-Fock equation. Now, we are heading toward extracting the physical meaning of the Lagrange multipliers. Is there a Lagrange multiplier in this equation? Yes, it is the epsilon I. Epsilon I is minus lambda I, right. So, since we have done the diagonalization, you do not need the row index and the column index, it is the same value along the diagonal element. So, there is a single index which is the ith index, and this epsilon I is really coming from the Lagrange multiplier. So, this is what you have got. Now, let us take an example of a 3 electron system just to get some feel for these numbers. So, for the 3 electron system, the energy expression which we wrote on the previous slide, this will add up to these integrals. There are these 1 electron integrals, which is the matrix element of the 1 electron operator in the state 1, 2 and 3, and then there will be pairs of terms, the Coulomb minus the exchange, which is how they come in pairs, right, the Coulomb minus the exchange between electron 1 and electron 2, electron 1 and electron 3, and electron 2 and electron 3, right. So, this is the total energy, okay, going just by the complete expression that we had for an arbitrary value of n. So, we will just specialize it for a small system like the n electron system. The specialization we are considering is for a 3 electron system, just to take a very small system and to see what it does. Now suppose from these 3 electrons you remove 1. So there is in quantum state 1 there is 1 electron, in quantum state 2 there is another electron, and in the third quantum state there is a third electron. Okay, there are 3 electrons. You remove the one in the middle, pluck it out. How would you do that? You will have to supply some energy to the system because it will be bound to the system. So you have to overcome the binding energy. You can do so by having electromagnetic radiation of appropriate energy shine on it, and once the atom absorbs it, the electron in the particular subshell can be removed. Like if you have the lithium atom or beryllium atom, beryllium has got 4 electrons, and if you give energy as much as the binding energy of the 1s electron, you will remove the 1s electron from the beryllium. Okay. So you remove the electron in the quantum state that we have labeled as 2. Mind you that each quantum label is actually a set of 4 quantum numbers here, whatever they are. Okay. They could be n, l, ml, ms if you like. So there are 4 quantum numbers. Each quantum number, each index over here, whether it is 1 or 2 or 3, is a set of 4 quantum numbers, and you are creating a vacancy by supplying some external energy to the atom and creating a hole in that state in the n2 equal to. So the occupation number of the quantum state 2 will become 0. So n2 becomes 0. So this is a 2 electron system with n2 equal to 0, but n1 is equal to 1, n3 is also equal to 1. So you are not touching those quantum numbers. Okay. What you are assuming is the frozen orbital approximation. Okay. When you are creating this cavity, one would expect that the other orbitals flex, they would relax. Okay. Those charge densities will also be affected, because removal of an electron is removal of an electron charge, and you have got a certain charge. There are 3 electrons in a certain region of space, out of which 1 electron has been scooped out, and therefore the remaining 2 electrons would have their probability amplitudes functions and the probability densities, they will need to flex and readjust because of the removal of 1 charge. And the frozen orbital approximation tells us that we are going to pretend in this approximation that these other orbitals do not flex, they will remain as they were when you considered the 3 electron system. Okay. That is the essence of the frozen orbital approximation. So then the same integrals 1f1, 2f2, this wave function for the state 2 is not going to change, and then you are left with these 3 terms, because n2 is equal to 0. Okay. So there are no pair interactions between electron 1 and 2 or between 2 and 3, because electron 2 is the one which has been removed, and you are left with only the pair terms between 1 and 3, and then the 1 electron integrals for the 1 and the state 3. So this is what you get for the 2 electron system. Now if you take the difference, just subtract this from what is at the top. So E psi 3 minus E psi 2, what do you get? You take the difference, cancel the common terms, and the reason you are able to cancel them is because of the frozen orbital approximation. Okay. If the orbitals were not frozen, you could not cancel those terms. Now under the frozen orbital approximation, you cancel those terms and you find that on the right hand side these 3 terms are nothing but what epsilon k represents in the Hartree-Fock equation. Now, epsilon k had entered our analysis via the Lagrange multiplier. It is just a name. Epsilon k is minus lambda k k, right, and because you do not need two indices, it is lambda in the diagonal form, there is a single index k. So, epsilon k is the Lagrange multiplier, this is the variational parameter, and this gives you, on the right hand side it is epsilon 2 which is the Lagrange multiplier, on the left hand side you have got the energy difference. This is the energy difference between the 3 electron system and the 2 electron system, and it is exactly equal to the energy that you have to give to pull out the electron from the state 2. In common terms, it is the ionization potential for the state 2. Okay? It is the binding energy of the state 2, it is something that you can measure, okay? And this is related to the Lagrange multiplier epsilon k within the applicability of the frozen orbital approximation. So, this is the key result, that if you generalize it not just for a 3 electron system, but for an n electron system, you remove one electron from the kth state. So, n k equal to 0, all the other occupation number remain the same. The energy difference between these two, which is actually the ionization potential of the kth state, the binding energy of the kth electron, this is exactly equal to epsilon k, which is the kth Lagrange multiplier, or minus of that, epsilon k is minus lambda k k. Now, you can develop this generally, means I illustrated it for a 3 electron system, and it is easy to write it for an n electron system, and the way to do it is to multiply these terms by the occupation numbers Ni and Nj. Ni is the occupation number of the ith state, Nj is the occupation number of the jth state, and these occupation numbers, because these are Fermi particles, these occupation numbers will be either 0 or 1. Okay? They can be only either 0 or 1. So, you have the energy of the n electron system, you can write the corresponding expression for the n minus 1 system, which is a completely identical expression, except for the fact that all terms for which Ni is equal to Nk, for which I is equal to k, that Nk would be 0, and those are the terms which will be removed. Okay? And you are summing over all the other indices, all the other states, only the one for I equal to k is 0, and if you then take the difference, you find that it will give you the kth Lagrange multiplier. Okay, what I illustrated for the 3 electron case is generalized here for the n electron case, and the difference between the n electron system and the n minus 1 electron system, which has got a hole in the kth state, which is the ionization potential of the kth state, is then equal to the kth Lagrange multiplier in the diagonal representation. This theorem is known as the Koopmans theorem. Koopmans has been written correctly, there is no apostrophe s, that s is a part of his name. Okay? So, if you want to put an apostrophe, it will have to be after this s, okay, not before. So, this is called as the Koopmans theorem. A very interesting person, Koopmans, student of Kramer's, and Kramer's suggested this problem to him, which he solved, and he wrote a paper in Physica, and this is presumably the only paper he wrote in physics. And then he nevertheless was a very smart fellow, and he went on to get what is the equivalent of the Nobel Prize in economics. So, he got This is not called as a Nobel Prize, but it is called as a Swerig-Rigsbank Prize in memory of Alfred Nobel. So, it was not instituted by Nobel, but instituted in his memory, and it is considered to be an equivalent to a Nobel Prize. So, Koopmans got this prize, but not for this theorem, but this theorem is a very powerful theorem, and we will address some other questions connected with the Hartree-Fock equation. We also asked if this is an eigenvalue problem. It does have some similarity with an eigenvalue problem, because on the right hand side you have got an energy kind of term, right. We already know that this is energy, it came as the difference of En minus 1, right. So, it is an energy term. So, the right hand side looks like the right hand side of a typical Schrodinger equation at psi equal to E psi. Okay. The left hand side is an operator, the one electron operator operating on the same function. So, it really looks like an eigenvalue equation. The Coulomb term also has a similar structure. You can see that if you just look at this box, everything whose argument is 2, R2 is integrated out. So, you are going to have an operator which is just a function of 1, okay. 2 is the dummy index which gets integrated out, and then you sum over all j, and then the Coulomb term also suggests that you can put it in a form so that an eigenvalue equation would possibly develop. But then if you look at the exchange term, there are other issues, because what you have over here is ui, which this is for the same quantum state I, which is on the right hand side, but the argument for the ith quantum state is R2 and not R1, okay, right. So, we have to be careful in handling this term. So, what we will do is first multiply this by this spin function, okay. This whole equation we will multiply by this. So, when you multiply this term by the spin function, what do you get? You get the complete spin orbital. This is the orbital part, you have multiplied it by the spin part, you get the orbital, the complete spin orbital, and therefore, the argument is written as q1 instead of r1. R1 is just a set of 3 space coordinates, q1 is a set of 4 coordinates corresponding to the 3 space coordinates and 1 spin coordinate, right. So, by multiplying this by the spin function, you get uiq1 here, likewise you from this uir1 you get uiq1 here, on the right hand side from this uir1 you get the uiq1 here, and here you have multiplied it by this spin function which I have written as it is, okay. So, this is what I have written as it is. All the other terms wherever I could write this spin orbital as a product of the orbital part as well as the spin part has been written already. So, let us look at this operator in the box, and this operator is sometimes referred to as the direct Coulomb operator, okay. This has got the index j, it is specific to j, what is inside this box is specific to j, but then you can sum over this j and get 1 which is summed over all the particles. So, this is the Vj operator, this is the Coulomb operator. Using this you can write this equation in a slightly compact fashion, because this involves integration over the space variables and summation over the spin. Now, what is the summation over the spin part? 1 over r1 2 has nothing to do with spin. So, you carry out the spin over the spin coordinate 2, both of these are states j. So, this is the spin state m as j zeta 2, and this is the complex conjugate of that, and you find that this is equal to 1, right. You have got the unit operator sandwiched between these two states, which is normalized. So, this integral reduces very easily to just the space integral, because the spin part gives you a factor of unity. Okay. So, the spin part gives you a factor of unity, and the direct Coulomb operator can also be written in terms of this integration over the space part alone. So, this is just a triple integral, whereas over here it is the triple integral and also a summation over the spin. So, this is the direct part, and using this direct part, this term can now be written in terms of this Coulomb operator, which is the V j direct. All the other terms have been written just as they were. The only difference I have made over here is to this term, which has now been written in terms of this V j, and then there is a summation over j that we will maintain. Let us bring it to the top of the next slide, and now let us define an operator which is called as the exchange operator. It is defined by this relation here. It is defined in such a way that whenever it operates on an arbitrary function of q1, okay, it will generate this quantity on the right hand side. That is the definition of the exchange operator. Okay. There is a certain exchange which is involved, that what appears in the integrand is phi q2, and then what gets multiplied or what gets operated upon is uj of q1. Okay. So, the j index is the same everywhere, wherever you have the 1 electron spin orbitals, the j index is always the same. So, this is j, this is j, and this is j. This is an arbitrary function of q2. This is the definition of the exchange operator, and since this holds for any phi, it will also hold for ui of q1. So, we will operate by the exchange operator on the ith spin orbital. Okay. Now, this is the spin orbital. So, when you operate on the ith spin orbital, in place of this phi q2, you will have ui q2, and this uj q1 will come here as an operand as before. This is your definition of the exchange operator, and using this you can see that here again you have an integration over q2, which is a triple integral over the space variables, and a summation over the spin, which can be done separately, because the 1 over r12 does not touch the spin part. So, the summation over the spin part is given by over here, and what is this? Here the index is j and here the index is I. So, you will get a delta msj msi out of this. So, in the when we dealt with a similar expression for the Coulomb or the direct term, we got unity. In this case we get a Kronecker delta, which will be equal to 1 only in the case of parallel spins, otherwise it will be 0, right. So, we can carry out the summation over the spin part separately and write this Kronecker delta, which is written over here. Then you have only the space integration left, because the summation over the spin part has been carried out. That is the one which gave us this Kronecker delta. The integration over the space part is just this integral with q2 replaced by r2, and the volume element dq2 replaced by the 3 dimensional space volume element dv2. So, this is your expression which you can now put over here, but then there is one worry, because here you had msi, but here you have msj, but that is not a worry, because this term is going to be non-zero only when msi is going to be msj, right. So, that will not create any hassle. So, let us do that. So, this is what we got from the exchange term, and then we can replace this term, this spin function for MSJ by the one for MSI, because it is non-zero only for parallel spins. Okay. And now we have exactly the term which appeared in the second term. What does it give us? You get the direct operator operating on UIQ1 minus, this is the minus sign, the rest of it is nothing but the exchange operator operating on UIQ1, and now you can combine these terms because you can both are operating on UIQ1, you can sum over j to give you this operator V with a superscript D for direct, and this operator V with a superscript X for exchange. Okay. And you have got this Coulomb minus the exchange operator, and you find that this is written in a form which looks like an eigenvalue equation. Okay. And in this form, and in Banstein and Joshain's book, they write very nicely that it is a deceptively simple form. It looks like an eigenvalue equation. If you looked at this equation, you would not doubt that it is an eigenvalue equation. You have got an operator operating on a function giving you a scalar times the same function, but it is not an eigenvalue equation. We know it from the very beginning, right. The reason it is not an eigenvalue equation is because of the exchange term, which is a global term. So, let us discuss this connection with the experiment further, because within the frozen orbital approximation we found that these difference in the energy, if you produce a hole in the kth state, which is ionization potential for the kth state, gives you the Lagrange multiplier, and you can therefore actually measure it. And I presume that some of you are doing some projects in material science or condensed matter physics, molecular physics, or some other branch of solid state physics, and you maybe produce some new materials, you want to characterize it, and one of the very powerful tools for material characterization is photoelectron spectroscopy, okay, which is also called as ESCA, the electron spectroscopy for chemical analysis. Is there anybody over here who has used it? Not yet, but some of you perhaps soon will. So, the electron spectroscopy for chemical analysis is a very powerful technique, and this was developed by Kai Sigman, who got a Nobel Prize for it in 1981. His dad got a Nobel Prize, I forget the year, but that was for X-ray spectroscopy, and Kai Sigman also got a Nobel Prize because he developed this technique. And what you do in this technique is, if you want to know, like, compare any two materials, you have something like gallium arsenide, if you like, okay, and you look at the energy of the 1s electron in gallium. Now, is the energy of the 1s electron in gallium the same as what it is in gallium arsenide? It probably would be different. How would you know that? How would you find out what the difference is? The way to do it is to expose a sample of gallium arsenide to electromagnetic radiation and find out the binding energy by checking the ionization potential. You do spectroscopy, okay, you do spectroscopy, do it over a range of electromagnetic frequencies or wavelengths, right. Usually these experiments are done using powerful light sources like the synchrotron, and using synchrotron radiation, or you can also use lasers or some other conventional laboratory light sources as well. You can do spectroscopy and find out what is the energy of the 1s electron in gallium, is it the same as it is in gallium arsenide. And if you do not know the composition of a compound, but you know that there is a certain atom which is present there, suppose you know that oxygen is present in a certain compound, and you want to find out what is its environment, and by environment I mean the physico-chemical environment. What are the other, has it participated in some chemical bonds? What is the physical structure? This is the crystallographic structure. What kind of symmetry is it in? Is it in octahedral symmetry? Is it in tetrahedral symmetry? What is the symmetry? That is the physical environment. And the chemical environment is what are the other atoms to which it is bonded. So, the physico-chemical environment will be responsible to shift the energy state of a particular electron. The 1s electron of oxygen will have different energies in different compounds. In sulfur dioxide it could be something else, in carbon dioxide it will be something else, because the environment is different. And by measuring this difference you would know what you are looking at. So, when you are looking at an unknown compound, when you produce new materials for technology, you want to know what is the composition. A powerful tool for material characterization is photoelectron spectroscopy. It is PES, sometimes it is done using X-rays, then it is called as X-ray photoelectron spectroscopy, or with ultraviolet radiation, then it is called as ultraviolet photoelectron spectroscopy. Sometimes it is called as ARPES, which is angle resolved photoelectron spectroscopy, because then you find at what angle has the electron come out. Okay. So, there are very many sophisticated offshoots of this technique, which is why it is such a powerful technique, and the Koopman's theorem connects it so nicely to the self consistent field theory, okay, within the domain of the frozen orbital approximation. But then of course, there are techniques to improve upon the frozen orbital approximation. I will mention some of it. So, now you know that this is something which relates immediately to experimental observations and to very important and very useful techniques. Mind you, this is not of importance just in atomic physics, but in all branches of condensed matter physics. Means you take a small piece of copper, if you like, a small piece of gallium arsenide, small piece of semiconductor, you want to know its band structure. How are you going to do that? How many electrons do you have in a small unit volume? You got like Avogadro number, right? Huge number, and they are all interacting with each other. And if you were to think of something like the chronic penny model, I assume that you are familiar with that, are you? Now, the chronic penny model is a single electron equation, which is so much remote from the physical reality of any many electron system. The solid that you are talking about, you want to get the band structure of something like gallium arsenide or some silicon or some semiconductor or some dielectric or whatever it is. It could be a metal, it could be a semi metal. Now, you have a huge number of electrons, and there is no way you can separate the dynamics of one electron from that of the other, because each electron interacts with the other electron through the 1 over R12 term. That is what we plugged in the Hartree-Fock theory. Okay? We had the 1 over R12, we had the antisymmetric wave function. So, the starting point for band structure calculations of solids or molecular orbital calculations in quantum chemistry, for everything the starting point for getting the electron structure is the Hatree-Fock formalism, which is why it is so important, and the Koopman's theorem is very important. But then one has to go beyond the Hatree-Fock, and there are many directions for that. Now, first thing is one should begin with the Dirac equation rather than the Schrodinger. Okay, what we did in the Hatree-Fock is to begin with the Schrodinger equation. So, when you do that, you get what is called as the Dirac-Hartree-Fock, and the Hartree-Fock formalism was developed in around 1928, 29, 1930, around that time. The relativistic self consistent fields, you know, some of the earliest work, I believe the first paper was by Walter Johnson in 1960, and then Declos and Grant, they also developed the relativistic self consistent field formalism around the same time. But then Walter Johnson went on to do so many other things. Grant focused on the many electron relativistic solutions, and right from 1960 until now, for 50 years he is working on the n electron problem, atomic and molecular problem, getting relativistic self consistent fields, and a huge technology. And I was mentioning it to someone over here that over these 50 years he would have worked with 50 young people, intelligent minds like you, okay, who have all contributed to the technology, and a number of PhD students, a number of postdocs. So in 50 years a whole machinery has been developed by Grant and his collaborators. Then you need to include the many electron correlations, and this I mentioned at the very outset, that in the Hartree-Fock theory certain correlations are included and some correlations are not included. If you remember, I had mentioned that the exchange correlations are included, and because of the frozen orbital approximation you have pretended the other electrons will not respond to any changes in the occupation of one electron orbital. Okay. So you need to go beyond the Hartree-Fock, because this is obviously an approximation. And the correlation energy is what you miss out when you do the Hartree-Fock, because in the Hartree-Fock, because of the frozen orbital approximation, you have left out the electron correlations, the Coulomb correlations, and these are left out in the self consistent field form. Nevertheless, you are able to write your wave function as a product of single particle wave functions. That is exactly what we have done. We have worked with an n electron wave function which is a product of one electron wave functions, right. What have we added to that? Antisymmetry. Okay. Our n electron wave function was made up of a product of one electron wave functions. The only thing we added to that was the antisymmetry. So we did include the exchange correlations, but we did not include the Coulomb correlations, and therefore one has to go beyond the independent particle approximations. The single particle model, it works beautifully, it does give excellent results, but then it has certain limitations and one has to go really beyond it. So you need to include many body correlations, and one does it by different mechanisms. The exchange correlations are also called as Fermi-Dirac correlations or statistical correlations, right, and the terminology is obvious. To include the Coulomb correlations, you can do what is called as MCHF, which stands for multi-configurational Hartree-Fock, or MCDF, which stands for multi-configurational Dirac-Fock. Dirac Hartree-Fock is the relativistic version of the Schrodinger self consistent field Hartree-Fock. Okay. Then there are other techniques which come from many body perturbation theory, MBPT. You can use methods of second quantization, quantum field theory, and this is a fairly large subject by itself, and this goes beyond this course. I am planning to address some of these techniques in another course which I will be giving in the next semester, in which I will discuss some of these techniques, the many body techniques. But at this point I would like to mention that you need more powerful techniques like second quantization, field theoretical methods to address those issues which go beyond the Hartree-Fock, which go beyond the frozen orbital approximation, so that you can include the Coulomb correlations. They are the ones which are responsible for the fact that the actual ground state is not the same as the Hartree-Fock or the Dirac Hartree-Fock ground state. Okay. you miss out on something, and what you miss out is typically called as the correlation energy. So, the subject is a very vast subject, and I will like to draw your attention to two excellent books, one by Walter Johnson and the other by Ian Grant, and these books have got a good summary of relativistic many body methods which are used in atomic and molecular physics. And Grant, as I mentioned, he has developed a huge technology over the last 50 years, and now there is a package which is what people use at the front end of atomic physics, which is commonly called as GRASP, which is a general purpose relativistic atomic structure program, and there are various versions of GRASP. This is a matter of detail for those of you who want to get into computational atomic physics, so you will be using some of these tools. There is amongst the other techniques I mentioned, there is this many body perturbation theory methods which were developed by Hugh Kelly, and there are so many others contributors to that. There is this random phase approximation and its relativistic version, the relativistic random phase approximation, and there are very many developments which go beyond the Hartree-Fock and also beyond the Dirac Hartree-Fock. So, essentially what we have is the relativistic version, which is the Dirac Hartree-Fock. Very often people call it as Dirac-Fock, and I must apologize that I also may have used the term Dirac-Fock sometimes, but as my friend and colleague and collaborator Vojar Radojevic always reminds me that it is injustice to Hartree not to mention his name. So, it should be called as Dirac Hartree-Fock and not just as Dirac-Fock. So, here the spin orbitals that we used in our analysis are the two component functions, right. Now, you are experts on relativistic quantum mechanics, which you did in unit 3. So, instead of the two component formalism, you can use the 4 component wave functions. Okay. And you have got the radial part, the g and the f functions, you remember them. Okay, we had them from the solutions of the Dirac equation, and then you had the spherical harmonic spinners. So, using these you can go through the exactly the same procedure, the same logic, and you would have effectively learned the relativistic Hartree-Fock as well. Okay. Everything is exactly the same. The whole approach to the relativistic problem is essentially the same. So, in one go we have essentially developed some familiarity with both the non-relativistic as well as the relativistic models. The only thing is that you have to make use of these 4 component functions. You will remember that we use these spherical harmonic spinners, and these are the ones which will go into the 4 component functions. So, using these you can develop the relativistic forms. Now, here you remember that it was this exchange term which prevented us from identifying this as an eigenvalue equation, right, because here the argument of the ith orbital is 1, here the argument of ith orbital is 2. Where is the argument 1? It is over here, and it is coming with the index j, and then the j index also has this R2 which is integrated over the whole space. So, it is a global term, okay, and it needs all the other solutions. So, this exchange term makes it impossible to write this operator as a function of just one coordinate. The Coulomb term, the direct term, could be written as a function of just one coordinate, which is q1, but you can't do it over here. Okay. We wrote it in a form which Branstad and Joshine call as a deceptively simple form, and the reason it is deceptive is because here you have got a global integration which involves the other solutions uj. Okay. So, this is the term which really makes it extremely difficult to solve the Hartree-Fock problem numerically. What you can possibly do is to develop a local density approximation, that is LDA, okay, that the exchange term, in fact it is a global term as you can see, because this is integration over the whole space, and you can develop some approximation to this exchange term, and these approximations are called as local density approximations, and using this you can develop approximate Hartree-Fock formalism, which also gives fairly good results, which is very useful in atomic physics and molecular physics and solid state physics. So, this is the local density approximation in which you make an approximation to this operator, to the exchange term, and this was introduced by John Slater. The first form was introduced by John Slater, but later on there are many developments following this. So, Slater's approximation is called as a free electron approximation, but that is a matter of detail. There are other variations like the X alpha method and so on. So, these are some terms which I am tossing over here for those of you who would read beyond the Hartree-Fock and beyond the Dirac Hartree-Fock, and the local density approximations are then the starting point for many more powerful but approximate techniques like the density functional theories and so on in many body problem. So, we need to conclude this unit 4 at this point, and I thought that I will mention some of these things for you to go beyond. There are a large number of contributors, and the most exciting problems in atomic and molecular physics are those which involve relativistic effects, electron correlation effects, and now you have some idea about what electron correlation effects are. A lot of work has been done by Alex Delgarno, Ugo Fano, Mike Seaton, and quantum chemistry, people like Jan Lindeberg have contributed a lot, Walter Johnson to atomic physics. So, a huge amount of development which goes beyond the Hartree-Fock and beyond the relativistic Dirac-Fock has taken place, and then the exciting problems are in atomic spectroscopy and collision phenomena, because what you have done here is to get the electron structure. So, this is what is called as the structure studies. Now, these describe the electron wave functions for the atomic system or the molecular system or the solid state system. Now, you have got this system. How is this system going to react to electromagnetic radiation, or how is it going to react if you bombard it by neutrons, or how is it going to react if you fire some other projectiles, because by carrying out these experiments you get a lot of information about the target, and that is what physics is about, that you have got a certain system, that is your target, how do you investigate it. So, you need to either shine light with it or bombard particles at it, and other than light and particles, what else do you have? Nothing, right. So, you do either spectroscopy or collisions, and at some level light and particles are also interconvertible, but that is a matter of detail, right. But either you need to do spectroscopy or you need to do collisions, that is the only way you can really probe targets. So, these are very powerful techniques. The Hartree-Fock and the Dirac Hartree-Fock tell you how to describe the electronic structure of the quantum system, of a microscopic quantum system, let it be an atom, a molecule, a solid, whatever. And then I will conclude this unit over here. The next unit will be on spectroscopy, and we will begin to acquaint ourselves with spectroscopic tools. Questions?
still why we cannot call that particular equation as an eigenvalue equation? Why it's a global term?
Because you really cannot solve it as an eigenvalue problem. An eigenvalue equation is not just how an equation looks, but also in how that mathematical equation is dealt with. It cannot be dealt with as an eigenvalue problem. That is precisely the reason Branston and Joshin call it as a deceptively simple form. It looks like, but it is not. Okay? That is the deception. You can make it look like an eigenvalue problem, but the operator that you really have, an eigenvalue equation is an operator operating on an operand, giving you the same operand scaled by some complex number, by scalar. Okay? This operator requires solutions to all the other n minus 1 problems, and unless you solve them, you cannot set up this eigenvalue equation, you cannot solve it as an eigenvalue equation. So, it can be solved only self consistently together with all the remaining n minus 1 problems. It is n coupled integral differential equations, and if you make an approximation to the exchange, you can solve it as an eigenvalue problem, but then you do not get the exact solutions. You do get useful solutions. So, Slater's approximation, which is sometimes called as the Hartree-Fock-Slater method or HFS, and since 3 names are associated with it, one tends to think that okay, this is something better than the Hartree-Fock, which it is not. Okay? It is Slater's approximation to the Hartree-Fock. Okay? So, there are various ways of the local density methods are quite useful, and what typically happens is that the larger the quantum system is, you need to have more approximations. The smaller a quantum system is, you can try to go for more exact solutions. So, it is not very easy to do a relativistic self consistent field for energy bands in solids, but yes, you can do it and people do it. Okay. So, do not get me wrong, you do relativistic self consistent field band structure calculations, you also do relativistic self consistent field molecular orbital calculations, but it is lot more common to see non relativistic approximations or local density approximations in molecular physics or condensed matter physics, because the more there is, the harder it gets. Any other question? Yes.
Now, is it possible by using generalized gradient approximation to get more accurate result here?
Well, you can get improvements using various alterations. Okay, there are so many different approximations that can be made, but remember what I mentioned at the very beginning of the discussion on the n electron problem, that a 3 body problem in classical mechanics has no exact analytical solution. When you put in relativity, you put in quantum mechanics, quantum fields, okay, even vacuum fluctuations, you do not have exact analytical solutions, you have to make approximation. Vacuum fluctuations, Lamb shift for example, if you start calculating the Lamb shift and then you make corrections, like for the hydrogen atom we talked about the spin orbit correction, then the kinetic energy correction, the Darwin correction, right. You start making corrections to the vacuum fluctuations, you make correction 1, correction 2, correction 3, correction 4, people have made something like 12, 13 corrections I think, and they still do not have an exact solution, and that is what is very nicely stated by Brown, who I quoted earlier, that if you are looking at exact solutions, having no body at all is already too many. Even for vacuum you cannot do it. So, there are a large number of many body methods which are developed, and that is where the challenge is. The challenge for a many body theorist is not to get the exact solution, that is beyond his scope, because there are existence theorems which tell you that the solution does not exist. What are you going to do? Okay. So, your challenge is to find the best approximation that you can, and there is a lot of competition in different approximation techniques, but then they also have their limited scope and range of applicability. So, I do not think anybody is ever going to claim that this approximation is going to give better results in general. I do not believe any many body theorist will make that claim, because you could get better results in some domains, but not in every domain. If you did, you would have something like a very general solution. That does not work, it is not that easy. I do not think we are anywhere close to it, at least in atomic physics, and therefore farther off in molecular and condensed matter physics.
Basically for homogeneous system.
LDA is an approximation, mind you, whatever it is. Okay, it is an approximation, it is pretending that the exchange interaction need not be treated exactly. Okay, but you know that the exchange interaction is there. The exchange interaction cannot be wished away. It is coming from the simple fact that electrons, your many body system consists of electrons which are fermions, and under an interchange of any two, the wave function must change its sign. Okay, you cannot wish it away, and if this interaction, which is the exchange interaction, is treated only approximately, it means that you are treating the statistics approximately. So, you are making a certain compromise, and by making compromise you are sometimes able to move ahead, which is useful, but not strictly correct, but it can be very useful. So, nothing wrong in using local density approximations. Any other question? So, thank you for now, and then in the next class we will begin with unit 5 on spectroscopy.